All right, so today we have Jonathan Heckman tell us about the higher symmetries of 5D Orbifold SCFTs. Take it away.
Okay, so first let me say thanks very much to the organizers for giving me the chance to talk at this Quiver meeting. I'll make sure to mention quivers at various points, but I will. It won't be a completely quiver-centric talk, but I will definitely make sure to mention quivers. So this is based on two papers, one of which has come out, and one of which is hopefully going to come out soon. So you can see here, one of them has already appeared. So this is with Michele Del Zotto, Robert Moskrov, Shani Nadir Minette, and Hao Zhang. So the first three are kind of localized around Uppsala, and Hao is a graduate student at UPenn who's going to be applying for jobs next year. So look for him. And in a paper that's going to appear hopefully very soon with Miriam Svedich, Max Hubner, and Ethan Torres, we're kind of continuing to look at some things. I'm primarily going to focus on this, but I just wanted to advertise this. So Max is a postdoc at UPenn, and Ethan is also a great graduate student at Penn who will also be applying for jobs. So look for him as well. So right, so these are the two papers that I'll be focusing on, and primarily just the first one. Okay, so here's an outline of what I'll try to cover. First, I'll try to motivate the class of questions I'll be talking about in the context of just quantum field theory in general. Perhaps I don't need to spend too much time on this for this audience, but I'll do it anyway. And then I'm going to move on to kind of the main technical object, which we're going to try and compute in various examples, known as the defect group for these certain kinds of quantum field theories, these 5-dimensional quantum field theories. And I'm going to explain the relation of that to higher symmetries of various kinds. And then we're going to try and see whether we can actually compute this thing in some examples. So the examples I'm going to focus on are 5-dimensional superconformal field theories generated from M theory on an orbifold background of this kind. So gamma is going to be a finite subgroup of SU3. We're going to quotient by it, and we're going to get a background which preserves in 5 dimensions, 8 real supercharges. And so in various cases, it will make a CFT. Then I'll move on to computing some examples, and then I'll go on to kind of tell you about kind of summary and future directions. Okay. So here's my motivation. The motivation is in some sense to figure out what is meant by quantum field theory when we use it as physicists. So it has a wide variety of applications across many different fields, not just high energy theory, but condensed matter, various areas of statistical mechanics, you name it, quantum field theory, cosmology. Quantum field theory often makes an appearance. And at least in terms of the textbook definition, we think we understand what we're talking about when we speak of quantum field theory at weak coupling. We can start from the free field description involving, say, some Gaussian fixed point involving just kinetic terms, and then we can start switching on interactions perturbatively to kind of gain access to this. And then you can ask, okay, how much of this does this actually cover in terms of the range of possibilities for possible quantum field theories? Are all such things described in some secret limit by some kind of Lagrangian field theory, or are we missing big chunks of possibilities when we make this assumption? In particular, we could ask, how restrictive is the requirement that we have a Lagrangian? And this could mean different things. It could mean that you have a Lagrangian, but it's practically useless. So you have some strong coupling dynamics you can't really speak about in any practical way. Or it could mean that we don't even know what the Lagrangian is, even in principle. Of course, quiver gauge theories count as Lagrangian field theories. So you might ask, well, I'm going to be heading towards strong coupling. What role could quivers possibly have? But we will see that quivers actually play a very important role, even in studying these strong coupling questions in many cases. So quivers definitely play an important role in that sense. But I'll come to the precise sense that we're going to use it later. Okay, so an important class of examples where things are kind of intrinsically strongly coupled are superconformal fixed points in more than 4 spacetime dimensions. So we know just from the classification of superconformal algebras that 6 is the maximal dimension. Nam showed this in the 70s. But constructing actual explicit examples is a rather challenging task because they appear to always be intrinsically strongly coupled. There's very simple no-go arguments that if you try to write down a Lagrangian and perturb that Gaussian fixed point, you're not going to make an example. So all the known examples as of today still involve kind of string-based constructions. So you take some brane configuration or configuration of cycles in a geometry, and you go to some singular limit to produce a limit where there's no mass scales or length scales in the system left over. Okay, so generating examples. So in more than 4 space-time dimensions, there's various machines you can use to build examples. So for 6-dimensional SCFTs, kind of a very kind of systematic way to start building cases involves F theory on elliptically fibered Calabi threefolds, where B is some 2 complex dimensional base. There's some torus or elliptic fiber sitting at each point. And the way we build the 6D CFT is by considering contractible curves in the base B. And the point is that the hallmark of the 6D CFTs that we know about involve taking D3 branes wrapped on those contractible curves inside of the base B. In the limit, those things make effective strings in the 6-dimensional spacetime. In the limit where it shrinks to 0 size, this is a so-called tensionless limit. It's still a local field theory, so in some sense, it's a little bit of a misnomer to call it a tensionless string, but it's definitely true that at generic points on the moduli space, you shrink these curves, and you're watching the effective string lose its tension as you reach the fixed point. And in the context of 5D CFTs, you can play a very similar game where you consider M theory on a Calabi threefold instead of F theory on a Calabi threefold. Now, because you're starting with an 11-dimensional setting, this will make a 5D theory. And I'll just point out, you don't have to even demand it's elliptically fibered. You can just talk about any Calabi threefold you want. And the way that you make a 5D CFT is by taking the limit in moduli space where you take a divisor or some kind of holomorphic 4 cycle, and you're shrinking that thing to 0 size. So we have M5 branes wrapping that 4 cycle. So we eat up 4 of the 5 spatial directions. We're left with an effective string in 5 dimensions. And this again produces a tensionless string, an effectively tensionless string. And this is the sense in which we can, this is kind of, again, the hallmark for making a 5D CFT. You're looking for these kind of effective strings. So as far as I know, all the examples that we have where we build a higher dimensional CFT have in some limit effective strings, which are losing their tension as you approach the fixed. That seems to be the hallmark. Okay, so this is geometrically how we build these things. And of course, there are brane constructions that you can also consider. An interesting feature is that many of these things also have kind of generalized notions of quivers, but that's not my main focus for today. Okay, so what can we compute once we have one of these strongly interacting theories? Well, one thing that the geometry definitely provides us access to is the moduli space of vacua. So we can ask about effectively flat directions and what happens if we give vacuum expectation values to various holomorphic operators. At more kind of, I feel like a microscopic or detailed level, we might also ask, can we enumerate various operators, including their scaling dimensions as well as their correlation functions? So things like the 2-point functions, the 3-point functions. If we were going to add, if we're treating this just as a kind of abstract conformal field theory, those are the kinds of things we would like to have access to. And lastly, as kind of a constraint or way to organize our thinking about these things, we can speak about different kinds of symmetries in these systems. So not just the superconformal symmetry, that's going to be ubiquitous, but more specific symmetries that depend on the particular kind of theory we're talking about. So I'm going to be focusing mainly on this one. So this can constrain, for example, the global form of the moduli space. It can constrain correlation functions. These are kind of classic applications. And in terms of things like anomaly matching, you can also constrain the RG flows. So if you have a symmetry which is not broken along a flow, then an anomaly has to match between the UV and the IR. This provides a good way of kind of constraining possible strong coupling dynamics. Okay, so now I'm going to move into what kinds of symmetries are we really talking about, and I'll mention we're going to be focused on like so-called generalized symmetries. And at some level, these are important in defining what we actually meant by the quantum field theory in the first place. So to a string theorist, you might say, well, come on, I gave you the string background, that's enough. But from a bottom-up quantum field theory point of view, you could ask, if someone tells you just the correlation functions and behavior for just the local operators, is that enough to unambiguously define what you meant by the quantum field theory in the first place? And so one of the things that's been appreciated more in recent years is that actually you do need to speak about the spectrum of extended objects in order to really get a handle on what the defining properties are. So you can have 2 theories that have exactly the same local operator content, but different extended objects. So this is important data in specifying what we actually meant by disambiguating different kinds of theories. So just as terminology, I'll refer to a 0-form symmetry as something that acts on kind of the local operators, a 1-form symmetry that acts on lines, and so on down the line. So you can think about this as the line could couple to a background gauge field by a pullback of a 1-form, onto its world volume, and that's why we kind of refer to it as a one form. And similarly for all the ones down. So you could talk about n form symmetries if you wanted to. And my primary focus is really going to be on the one form symmetries. Zero form symmetries are what we typically call just the usual global symmetries, but the one form symmetries tell us something about the extended objects in our theory. Okay, how do we determine these higher symmetries? So this is actually a very subtle question. And if you start writing down things in terms of Lagrangians, you can have various kinds of accidental enhancements, and it can be very tricky to actually figure out the global structure of the theory. Part of the issue here is that when you actually write down, like, say, the path integral formulation, we're implicitly working in terms of a kind of perturbative setup, and we're always imagining expanding around some saddle point. It's not providing like a non-perturbative definition of the field theory in the first place. So we don't actually write down all the configurations that we are supposed to sum over in the field theory. We just kind of say, well, we'll do perturbation theory about this or that weak coupling point. So it can be very subtle to kind of figure out this global structure. So there can be enhancements in these symmetries in the infrared. There could be de-enhancements, so things getting bigger, smaller, and so on. So I'm not really going to approach it in those terms, although that's definitely one of the ways that people have explored these things, especially in three dimensions in lower. What I'm instead going to do is focus on how to attack this question using the geometry of the string compactification. After all, the only way that we know that these 5D and 6D CFTs exist is via various kinds of compactifications. So it would make sense to see if whether the compactification geometry is able to detect this kind of feature. Okay, so now I'm going to move on to what I'm going to try and calculate in terms of these defects called the defect group. And I'm going to try to explain its relation to these higher symmetries we just mentioned. So maybe I'll pause here and ask if there's any questions at this point. Everybody happy? Okay, so let's keep going. Okay, so I'll again start with a 6D example, although again, I'm going to switch gears pretty quickly into 5D. In the context of 6D CFTs, again, I already mentioned how you make the CFT in the first place. Here I'm drawing the little base here. You have some curves that are collapsing. You wrap the D3 branes on this, and you get a dynamical effective string. And in the limit where that thing collapses to zero size, the effective tension is going to zero size. So the tension is controlled by the volume of the sphere that you're wrapping. So here's a little picture. We have the 6D directions here, and then we have 2 in the extra direction. So the 6, 7, 8, 9 is in the base directions. And we're imagining this thing wraps these 2 directions. Looks like an effective string in D3, sorry, in the 6D spacetime. And the limit we're taking to get the tensionless string is where the sphere collapses. But you can also consider things where it doesn't collapse. So here's a defect, something that's non-dynamical in the 6-dimensional theory. So instead of wrapping it on a direction that's going to collapse, let's instead consider, so I'm drawing it as kind of a, I don't know, red triangle, something that does not collapse to zero size. So what happens if we do that? Well, even in the limit where we collapse these 2 spheres to zero size, this thing remains as a big non-dynamical object in the 6-dimensional theory. So what's the effective tension of this thing? It's formally infinite. Why is that? Because the volume of this thing is infinite. So if we take this D3 brane, wrap it on this non-compact cycle and ask, what kind of string did we make in the 6-dimensional spacetime? It's a non-dynamical object. It's a very heavy kind of probe object, if you like. Okay, so that's existing even when we go to the CFT limit. So remember, when we hit the fixed point, all the mass scales either have to go to 0 or infinity. And in this case, these ones that are wrapping the blue circles are going to 0, but the ones wrapping the red triangles are going off to infinity. Okay, so those are defects in 6D CFTs. What's the defect group? Well, we can now say, I want to talk about the higher symmetry. I want to talk about like the world volume 2 form potential, which couples to this D3 brane. You get that thing from just taking the 4 form potential of type 2b and dimensionally reducing it into the 6-dimensional spacetime. And some of these dynamical objects can in fact screen the charges coming from these non-dynamical objects. So we refer to the defect group in physical terms as the charge. So I should have inserted the word charge, but it wouldn't fit on one line then. The charge of these non-dynamical strings modulo the charge of the dynamical strings. So in some cases, you can screen pieces of the charge of the defect, but in other cases, we will not be able to. And what we'd like to do is be able to compute this thing. Okay. So more formally, what are we doing? We have F theory on a elliptically fibered Calabi threefold with a non-compact base B. The defect.
Can I interrupt with a question, Jonathan?
Yes, please.
So just to be clear, the non-dynamical objects might be not mutually local. Is that correct?
Correct.
Okay.
And in fact,
So
in
you're
6 dimensions,
including
it's
all
even
of
more subtle because if you like there can be a non-trivial braiding, and that's actually what's being captured by this defect group, if you like.
Okay. Thanks.
Okay. Great. More questions? Okay. So so in this very simple setting, what are we doing? We're saying I want to talk about two cycles which extend out to the boundary. So I'll write that as H2B, and I'll write it as a relative cycle. So this is a thing that could be a 2-chain, but it has to end somewhere on the boundary. That's all I mean by this partial B thing. And then it's modulo the kind of spectrum of objects we get from things wrapped on compact cycles. I'm denoting that by H2B. So these are the ones where it's wrapped on the compact circles. Sorry, there's 2 spheres. So can we compute this quotient? Indeed, we can. It's calculated by this relative homology sequence, exact sequence. So this kind of continues on forever, and you just keep shifting the degrees. Hopefully you can see the pattern. So here I think you can figure out what would go. It'd be another H1, but a relative type. And up here, we would have somebody else involving the appropriate H. Okay, so can we calculate this thing? In this simple example, yes, we can. So it turns out that all the bases for 60 CFTs take the form of orbifolds of a finite subgroup of U2, not SU2. The reason you preserve supersymmetry has to do with having a non-trivial elliptic fibration. So the total space, the Calabi-Yau threefold, is still Calabi-Yau, but the base doesn't have to be Calabi-Yau. And you can go ahead and calculate what the defect group is in this case. So it's calculated by this thing here, H1 of the boundary. So the boundary of the C2 is just a 3-sphere. You're quotienting by this group action. It doesn't have any fixed points. And so just from general properties of how homology is related to the fundamental group, you can read it off as the abelianization of that group here, gamma. So you just impose, you take that group gamma, and you say, I demand that all the commutators kind of become trivial. Okay, so we can calculate in all these examples what is going on. Now, an important point about this is that this actually demonstrates that the data associated with this defect group is really stuff that's intrinsic to the CFT. It doesn't require us to know anything about how the geometry was resolved or blown up or anything like that. There could have been multiple ways of resolving the Calabi-Yau threefold. None of that information enters in speaking about the defect group. It's all controlled by the orbifold group action, namely at the limit where we crushed it, all this 2 spheres to 0 size. So this is the sense in which the defect group really is capturing properties of the CFT rather than just some geometric phase where we resolve and gone onto the moduli space. Okay, so more generally, you can state this quite a bit more generally compared to, so we did it here in the 60 CFT context, but then it was figured out in, I think, this pair of papers that you could do it in a much broader context by just talking about, say, your favorite M theory, type 2 construction, and so on, where you again start writing down over here, these quotients of relative cycles modulo the compact ones. And you basically get some summation like this, and you just have to figure out what N you're talking about. Those are going to act on the various kinds of extended objects. And once we have that, then we can say, okay, quotient that, take all the different P branes that could contribute, and build up the corresponding spectrum with defects. So here's my picture of how that looks. We have the singularity. It's kind of localized at the tip of a cone, and it extends out, and here's the boundary. What do the defects look like in this setting? They look like things that are stretching from that singularity all the way out to the boundary. Okay, so the ones that are going to get screened are the ones that are just wrapped on compact stuff in here. That's the stuff associated to HK of X. And the ones that don't get screened are the ones that are kind of left over from those relative cycles. So we again take all the relative cycles, which can extend all the way out, modulo the compactly supported stuff. Somehow I've done something to the Zoom toolbar. Sorry, let me just. There. Okay, it's back where I wanted it. Great. So that's what we do for the more general defect group story. Okay, so what does this have to do with higher symmetries? So these defects that we just introduced are acted on by the higher form symmetries that we just mentioned. So to see how that comes about, we have to kind of split things into kind of an electromagnetic basis for the defects. And this amounts to what's called a polarization. So in practical terms, right, remember just back to quantum mechanics, what do? I can tell you about the position of a particle, or I could tell you about the momentum, but I can't tell you simultaneously about both because they have a non-trivial commutator. A similar thing happens in this context where if I tell you the electric basis of states, I can speak about the charges there, but then that's specifying a polarization for me. I'm not allowed to then also tell you the corresponding magnetic basis of operators. There will be a non-trivial braiding between them. So this higher form symmetry is kind of acting as, like, if you like, the electric one form symmetry, and I'll contain it in this thing D, this defect group that we're going to compute via geometry. So just as a small technical aside, it's actually the kind of, if you like, the Pontryagin dual group. The reason is because, you know, it's a question of like, are you talking about the group and how it acts on the objects, or are you talking about the thing that is being acted upon? This technical aside doesn't really matter too much for what we're going to talk about today, because the Pontryagin dual is isomorphic to the original group because everything is a finite cyclic group that I'm going to talk about. So it's not going to matter too much, but just as a technical aside. Okay, so that's the relation between defect group and higher symmetries. So the name of the game is in some sense to compute this D. So can we compute this? Okay, so in the earlier papers where they proposed this as kind of a general notion of what you meant by defect group, you know, it's not as easy to calculate it as it was in the 60 CFT context. Why is that? Well, what do we actually mean by these homology groups in the first place? We're talking about highly singular geometries, right? We've collapsed a bunch of things to zero size. And so you could ask me, if I hand this to a mathematician, what would they say? Well, first of all, you're talking about a singular space. What do you mean by the homology groups? So what would you do in practice? One approach is perform the explicit resolution. So this is a Calabi-Yau geometry. We're expecting in the case, at least of Calabi-Yau threefold, to be able to do Crepin resolutions to kind of resolve all the singularities. But it's not guaranteed that it's going to be, first of all, you know, practical in all cases to get this off. And second off, you know, there may even be cases where, you know, we just don't know how to do the resolution in a nice way. So
aren't these homology groups well defined for singular spaces?
There's versions of them that are well defined, but you have to be very, yeah. So there are indeed versions of these things that are all well defined.
I mean, regular singular homology theory would be defined, but you're saying that might not be the right homology theory?
Yeah, well, that's one of the things we have to check, right? So there's other notions of homology which will spit out different answers for the homology group. So, you know, which one do you want to talk about?
I see. Okay.
So indeed, singular homology is usually good enough for our purposes, and that's the one that matches to all the resolution independent stuff. But I think there is a natural question here about, you know, okay, what do you actually mean by this in all cases?
Singular homology is intersection homology. Is that the same thing?
No, it's just if the space was, for instance, triangularizable, be the usual the usual combinatoric definition of homology in terms of chains and cochain. But it can be done for a general topological. That definition works for a general topological space, but it might not be the right.
Well, okay, so let me give you an example where I don't know the answer. Suppose that X has a terminal singularity. So I don't know in that case what the right notion of homology we're supposed to use is. So you can do a blow up, for example, but that when you do those blow ups, you can get rid of the singularity, but you'll violate the Calabi-Yau condition. So you'll get an answer. I don't know if that's the correct answer physically, though. So that's an example.
But in that case, you could do deformations. And in fact, if you have a terminal singularity and you look into B and use deformations, you actually do get exactly this kind of defect group that you require for, say, the one form symmetry.
Mm-hmm. Yeah, my point is simply that it's not a priori obvious. You've got to do more. So in the case you're talking about, it wasn't just a straight blow up, right? You also had to do smoothings of various kinds and so on. So
yeah, I mean, sometimes you have to look at deformations of the singularity, but it's some kind of smoothing one way or another.
Right.
Do we know that the defect group is preserved under deformations? In other words, I'm thinking of.
I mean, it should actually not depend at all on what you do, right? That's, I think, also the point of the talk. It's just, if you want to explicitly calculate it in this way, then you might need to have some notion of, you know, a smooth model for this.
Well,
but I think one other way of thinking about it is just think in terms of the boundary of the space, right? So the idea is it should not depend how you've smoothed it. In fact, it shouldn't depend on whether you calculating it on the Coulomb branch, fully resolved, or on the partially resolved Coulomb branch, or the fully singular model?
In terms of, maybe I'm just misunderstanding. In the situations that I know of, like a deformation might have to do with, say, physically a mass deformation, and global symmetries change as soon as I turn on mass deformations.
That's true. So you want very specific deformations.
I see.
That
So you're saying that there's a
are
certain
part of
class.
what we call versal deformations.
I see. Okay.
But sorry, if you're looking at a threefold, the homologies are very different if you resolve or deform. So I mean, if you take the conifold, you're either going to grow a 3-sphere or a 2-sphere, depending on which way you go. Isn't that going to drastically alter your group?
That's true. But I mean, in these cases, for example, right, you might, in M theory, you might be interested in 2 cycles, right? Non-compact 2 or relative 2 cycles. And M theory, you might be interested in to be in a total different set of cycles, which you can generate from the deformation.
Okay.
But anyway, I think Jonathan's point is all this is, you can forget about it and just think about sort of the boundary of the space.
Yeah, I mean, okay, so first off, I think that there are indeed all these subtleties with, you know, the homology groups jumping depending on how you deform it. But then on top of that, the question is, you know, just in practice, you got to do the blow-ups if you want. And, you know, that by itself is a pretty complicated task in many situations. So the key point I'm trying to make, though, is that at some level, the physics should not care about how you, if you've done it correctly, it shouldn't care about any of that, because this is stuff that's supposed to be intrinsic to the CFT. All it really relied on was having that singularity there in the first place. So can we go ahead and compute this? Okay, so I'm going to focus on some tractable examples coming from M theory on the following kinds of orbifold singularities. And I want to make a 5D CFT, so I'm going to demand a collapsing divisor. So I'm not going to take, you know, kind of, you know, silly examples like gamma just being a proper subgroup of SU2. I'm really going to demand that it kind of fills out a genuine, like a SU3 subgroup. And when we do this, we get a 5D SCFT. And a nice thing is that these kinds of singularities, the groups and the corresponding, even the hypersurfaces associated with them, hypersurface singularities associated with them, were worked out long ago. Okay. So now I'm going to move on to 5D CFTs via these kinds of orbifolds. Okay, so how we want to calculate this. Okay, so I'm talking about M theory. So I got 2 objects to discuss. One is M2 branes and one is M5 branes. I'm mainly just going to focus on the M2 branes. There's a parallel thing you can talk about for the M5 branes, but as we'll see, it's actually redundant information in these examples. So I'll focus on this, and we're going to try and figure out a way to compute this quotient here. Okay, so let's calculate this thing. I'll call it the electric one form, even though there's not much of a distinction here in 5D. What's the boundary geometry we're talking about? It's a 5-sphere quotiented by this finite subgroup of SU3. Okay, so sometimes that finite subgroup action has fixed points. In fact, that's kind of a typical situation. Now, if you remember that 6D CFT example where I was quotienting by a finite subgroup of U2, a very nice feature of those examples is that there weren't any fixed points. And so it's very easy to read off this kind of quotient via a relative homology sequence. In these more complicated situations, however, there can be fixed points. And so saying, oh, I just know it's the abelianization of gamma turns out to be wrong, because it's not a fixed point free action on the boundary 5-sphere. So we're going to have to figure out how to deal with that complication. Okay, so I'm going to tell you 2 approaches for calculating this thing. I'll refer to these, roughly speaking, as the Quiver approach and the algebraic topology or pi1 approach. And okay, so now I will talk about quivers in some form. So in case you were anxious that I was going to drop the theme. Okay, so let's talk about the Quiver approach to calculating this thing. And this goes via 5-dimensional BPS particles. Okay, so suppose we take our 5D theory and stick it on a circle, but let's try and retain all the Kaluza-Klein modes. What would we get? Well, since we're dealing with M theory, we know that the Kaluza-Klein modes descend down to the 0 branes of the type 2A string theory background, right? So remember, M theory on a circle gives us type 2A string theory. So what do these particles look like? Well, they're BPS objects, and they're D0 branes, and they're probing the orbifold singularity we're talking about. These things are directly sensitive, as is well known, via Quiver quantum mechanics, to the homology or some notion of the basis of fractional branes we can wrap on various 2 cycles and 4 cycles in this C3 mod gamma. And of course, depending on how we, blow it up or, mutate the quiver, we can get different chambers of how this quiver will look. But the key point is that this quiver gauge theory, this quiver quantum mechanics, I should say, knows about all of that geometric data associated with H2x going to the boundary and H2 of x. And to reinforce the point even more, if you then take that 4-dimensional theory you got from type 2a, and you imagine compactifying further on a 3 torus spatially, you could T-dualize that thing and turn the D0 brane into a D3 brane. And then you have a D3 brane probing that same orbifold singularity. That's a quiver gauge theory in 4 dimensions with n equals 1 supersymmetry. Okay, so quivers. I probably do not need to spend any time on this for this crowd. Okay, so quivers, many people worked on this and figured out kind of a general algorithm for how you would, the machine that you would use to read off from a given orbifold singularity, what the corresponding quiver gauge theory would be. So here's just a simple example, D3 brane at C3 mod Z3. This one's easy enough that we can also just resolve it almost by hand. It's just the canonical bundle over P2 or a line bundle of degree -3 over CP2. And we have 3 arrows going between each of these little nodes. Okay, so that's our quiver in this particular case. So that's it. So by the way, C3 mod Z3 is a perfectly good, defines a perfectly good 5D CFT. It's this celebrated E0 Seiberg theory. It doesn't have a Lagrangian description in 5D, but we know that it's producing an interesting fixed point. You can connect it to a whole chain of other 5D CFTs. And yeah, you can also see it in 5 brane wrapping the collapsing P2. So it's got all the trademarks you need of a 5D CFT. Okay, so given a quiver, we get a directed graph, the adjacency matrix. And an important point is that in the 4-dimensional theory, this adjacency matrix is telling us about a Dirac pairing for BPS states. So we can split things. Well, I guess I should have put a little thing involving the flavor charges too. So there's the kind of the dynamical ones, and then of course there's the flavor ones. Those flavor ones are of course quite important for the non-compact bit of the story. But the point is that you can split the charge lattice into electric and magnetic states. And via a fact about this adjacency matrix, so some of that is going to appear, I understand, in a paper to appear soon, you can actually work out the corresponding defect, the one-form symmetries for this system directly from the Dirac pairing on the BPS states. So it splits into 2 one-form symmetries. I'll call those G electric and G magnetic. And just mathematically what we do is we feed in this adjacency matrix, and we're looking at the torsional part of the co-kernel for this, this matrix A. So geometrically, this actually matches directly to what you typically, or what was done in the past for calculating this thing, where you resolve the geometry in some way, you'd start looking at H2 and H4 for that thing, and you'd compute the so-called Smith normal form for the intersection pairings. And then from that, you would then read off the exact same statements about the electric and magnetic one. And we can see that this matches to the prescription here. So just remember, the quiver is kind of encoding all of the data about intersection theory for that singular geometry in the via the adjacency matrix. Okay, here's an example. So I'll just go back to my C3 mod Z3 example. What's the adjacency matrix here? I hope I didn't screw this up too badly. You can clearly see a number 3 everywhere, right? That 3 just dumps out a Z3 for a bunch of things. That's all. So basically, you know, you're looking at some torsional piece, and that 3 directly tracks with the Z3. For the more complicated ones, there's a bit more work to figure out the corresponding Smith normal form for this thing. But that's the rough idea. Okay, so this in 4 dimensions gives us a one-form symmetry of electric and also of magnetic type. And you could ask, what does this lift to if we go back? So that was for the 4D Kaluza-Klein theory, where we retained all the Kaluza-Klein excitations. And you could ask, what's going on in 5 dimensions? It lifts to a one-form electric symmetry. That's from the M2 branes wrapping things. And you also get a magnetic 2-form from the M5 branes. And it turns out that they're equal to each other. It also turns out that in all the examples, one can directly show that the electric one-form and the magnetic one-form are always identical. So in some sense, it's redundant information, as I mentioned earlier. To talk about both the M2s and M5s, all we have to really focus on is this one. And then the other one will just be spit out because it's redundant data for these examples. Okay, here's some more sophisticated examples. So what are these?
Jonathan?
Yes, please.
If you look at this example and you look at the case where you compute the F-flat moduli space, but not taking the gauge invariant combinations, right? So you get a 5-dimensional space, which is a cone over 2 P2s. And then in this case, so you could also describe it like a U1 gauge theory with the 3 charge +1, 3 charge -1 objects. So that's your 5-dimensional theory. Sorry, 5-dimensional space. If you impose gauge invariance, then you'll get the C3 mod Z3. Now, the point is that you have those 2 P2s, and I'm wondering if there is any connection for the 2 P2s with these electrical magnetic symmetries that you computed here.
Yeah, this I don't know. I'm tempted to say it's not related. The reason is that how do we get the quiver nodes from the geometry of the C3 mods O-3 over P2? So remember, one of them is coming from like, the D3 brane kind of spread over everybody. Then there's the CP1 inside the P2, and then there's the other one, there's a P2. So the different nodes of the quiver are being treated on unequal footings. And so my worry is that if I try to interpret everybody in terms of just the P2s, then I will kind of be forcing I'll be forcing everything onto an equal footing when it's not necessary. But I haven't really thought about it, so I will think about it, but I don't know the answer.
Yeah, but
to say it's not related, but
you just want to take into account that those nodes, the blue nodes, are not just points 1 cycle, 2 cycle, and 4 cycle. It's a linear combination of them.
That's right. That's right. So the quiver is more clever than just saying, oh, it's a 0 cycle, 2 cycle, and 4 cycle. Yeah. Yeah.
Okay.
Yeah, but I don't know the answer. So it's an interesting observation. I will think about it.
Okay. Thank you.
Okay. Okay. So that's my one simple example here. Here's a set of more sophisticated examples. So remember I told you about finite subgroups of U2. Okay, I can also do the same thing for the 5D CFTs. So what do we do here? We imagine that we have like a 3x3 matrix. We decompose it into a 1x1 block and a 2x2 block. We stick the U2 in the 2x2 block. And then whatever we get for the determinant of those, entries, we can compensate the phase in the 1x1 block by adding the inverse of that phase. And so we can always stick a U2 subgroup inside of an SU3 in this way. Okay, so here I've just listed some particularly nice examples. So the U2s, roughly speaking, there's an ADE type classification you can speak about for these. So T is the, what's the terminology here? T is for like a generalization of E6. O is like a generalization of E7, and I is like a generalization of the E8 finite subgroup. And these little m's tell us how much we're twisting by the kind of overall U1 factor associated with U2. And then there's a corresponding D series. I'm not talking about the A series because that's, again, just abelian and so on. So we can go ahead and we can calculate. Here's the order of the groups. You can see that it just kind of pulls out this little m here like that. And you can actually also calculate, just using that quiver trick that I told you about, we know how to get the extract using well-known quiver methods, what the corresponding quiver gauge theory is for each of these cases. Go ahead, calculate the torsion of the co-kernel of the adjacency matrix, and you get these answers for the defect groups. Okay, and then you can see that there's interesting divisibility conditions depending on whether m is, prime or relatively prime or not to 3, for example, in this case, and 2 for this one. Okay. And you can, of course, do more examples of this kind. And, you can consider much more elaborate, finite group actions. Many of these were studied by Ami and friends in the late 90s, I think, for what the corresponding quiver is, and we can basically borrow all of those results to then start calculating these higher symmetries for these 5D CFTs. Okay. Now, yes, please.
Can you say a few words about this notation that is used?
Which part? This one here?
Yeah, 3/m and
Oh, 3 divides m.
3 divides them and does not divide them. I see.
Correct. So,
Okay,
so you get a
okay,
different
okay.
answer depending on whether it divides or doesn't divide.
Okay, very good. Thank
Yeah.
you.
By the way, a similar divisibility condition was actually observed. It's not too shocking in the 60 CFT case where you calculate the defect group. It just has to do with the fact that if you take like, SO groups, the center jumps around a little bit, depending on whether it's SO even, it goes in multiple steps of 4 rather than 2. So it's a similar phenomenon here. Okay, more questions? Okay, so now after telling you how wonderful the Quiver approach is, I'm now going to say what's not so wonderful about it, which is that you have to work kind of hard to extract a corresponding quiver in each of these cases, right? So I was complaining earlier that, it's so painful to compute these resolutions of the Calabi-Yau. Wouldn't it be nice if there was a way where I didn't have to do any, I could just be quite lazy and get the answer correctly. Okay, we did the Quiver approach. That seems to help us. We don't have to do any blowups, but you still got to compute this quiver in the first place and then do all this other machinery to extract the defect. Is there another way for us to go? So there's a complementary approach, which we can use, if you like, as a cross-check on what we just said for the quivers. So the quivers, it's an interesting, I would say it's intrinsically interesting because it's telling you about the BPS particle spectrum of this system. So that's a very nice thing. And as another benefit, it also tells you about the defect group. So what I'm going to do now is switch gears a little bit and start talking about a different way of calculating it, just using directly the topology of the boundary space, this S5 mod gamma, and the fundamental group. Okay, so I want to calculate this, this quotient here, and it's going to be related, just because of general properties of H1, to the abelianization of the pi1, the fundamental group of the space. Now, the tricky point here, as I already mentioned previously, is that this quotient may have fixed points. So it's not correct to say that pi1 is always going to be equal to gamma. Those fixed points are going to mess up that story. And I'll give you some examples of precisely how that happens. So this is going to work even when pi1 is, even when the group action has some fixed points. Okay. So here's a nice theorem that we can apply all the way back in, I think, 1967. I think I have the date correct. Armstrong demonstrated that you can just write down this thing is gamma mod n fixed. What is n fixed? It's the normal subgroup inside a gamma, which generated by elements which leave at least some points of the phi sphere fixed. Okay, so this is defining, one can show it's a normal subgroup. And so if I take the quotient, this thing is again a group, which it's got to be if it's going to be associated with pi1. But the point is that we're kind of getting rid of all the garbage I was complaining about previously, saying, I don't know how to calculate this because of the fixed points. Well, Armstrong's statement is that, okay, fine, quotient by that stuff, and you're going to be left with the actual fundamental group for the boundary sphere, mod gamma. So let's go ahead and do that. So in one line, here's what you get. You'll get the electric one-form symmetry is just the abelianization of that gamma mod n. And roughly speaking, in a lot of examples, that this fixed locus, you can think about it in many cases as just like the location of where some, if you like, flavor six branes in M theory are coming along. So they often have the form of like a C2 mod gamma. And so you get a flavor brane, if you like, in the in the 5D system. So it's like some non-dynamical 7D super Yang Mills, which is extending out to the boundary. Okay. Here's a simple example. We can calculate the group action. So let's take Zn, and here's the group action I want to talk about. So omega is a primitive nth root of unity. So you notice the determinant is 1, so it fits inside of SU3. When n is odd, there's no fixed points. And so, it's relatively straightforward to get out the defect group. It's just going to be Z mod n. Nothing to worry about. If n is even, then there is a fixed point locus. And you can see it because there's a generator where you take omega to the n over 2. So because I can divide by 2, I can speak about this thing. And you can see that if I set Z1 and Z2 equal to 0, there's a whole circle which is going to get fixed because omega squared trivializes on this, right, for that generator. So that's a Z2 subgroup. And the locus of that fixed locus is at Z1 equals Z2 equals 0 in the way I've written the group action here. So what do we get for the defect group in these two cases? Well, we get Zn in one case, that's for n odd. And when it's n even, we got to worry about that fixed point locus, but we can kind of get rid of that garbage in this way and read off a corresponding cyclic group where we just divide by 2. Okay. So that's a simple example. Another example. So this one was worked out using completely different methods in these papers here. We can consider a Zn times Zn. This is known to engineer the so-called 5-dimensional Tn theory with this choice of group action. So again, omegas and zetas are, I think the notation is self-explanatory. And in this case, the fixed point locus is so big that n fixed is actually all of gamma. So what do you get? You get gamma mod n, and you get nothing left. So we're predicting then that we get a trivial defect group in this case. There's so much stuff that's fixed by this thing that you just get nothing left over. And that agrees with what was found in these papers here. Okay, so the general idea or the general intuition is that as you start increasing the size of the orbits for gamma, you're going to pick up more things that might, get fixed, and you often get smaller electric one-form symmetry. Of course, we can also write down, infinite families. I gave you some examples where the defect group kind of persists to, arbitrarily high order. But the point is that, morally speaking, as more things get kind of filled in and fixed, you're losing the possibility of screening the charges associated with the one forms. Okay, that's it for that stuff. There's another kind of higher symmetry, which I want to talk about in 2 minutes. Okay, called two groups. There's lots of papers on this subject. It's kind of started getting a little bit more interesting lately. And so I'll just advertise here. I'm not going to talk too much about what's in this paper, but I just want to advertise that it will, I don't know, hopefully be done soon. Who knows? But there's these it's related to something. I'm mainly going to focus on the kind of conjectural observation that was made in here. Okay, so let's recall zero-form symmetries act on local operators, one-forms on line operators, and so on. But nothing stops you from saying that the lower form symmetry might in fact still be acting in some non-trivial way on the extended object. And this is kind of the hallmark of this intertwining that can occur. It's kind of the hallmark of what I'd refer to as an n+1 group. So the simplest case that we're going to talk about is a two group, namely zero form symmetry acting upon one forms and so on. Okay, so you can have local operators, you can have lines, and you can kind of stretch them here. This is my picture of two lines joined or getting jumped by a local operator. Lines can end on local operators, and lines can also change. And so kind of what we're after is a way of kind of encoding kind of genuine local operators where they can't just be defined by endpoints of lines, as opposed to those that just kind of like sit there in the theory by themselves and don't require a line for their existence to make sense. So all of this can be encoded a little bit more formally in terms of a collection of short exact sequences and a long exact sequence, if you like. Here it is. So this was, I believe these are the correct references. This was figured out in these papers here, where you write down kind of this tilde thing, which I'd refer to as kind of the naive defect group, and the naive global symmetry. This is the G tilde. And then there's the kind of genuine one that you actually get once you properly account for, screening and effects like this. So there's the defect group D1 right over here, and then there's all the rest of it that kind of comes along. And then you can take these two short exacts and kind of piece them together to form a longer exact sequence like this. Okay, so that's a nice story. And now you could ask, okay, great. Can we see any of this data in terms of anything we said in the previous parts of the discussion? In practice, what is often done in the literature, and that this seems to be good enough for basically all practical purposes, is you look at this short exact sequence, and what you're looking for is when this thing is not a split exact sequence. What do I mean by that? It means that D tilde is not just the direct sum of this plus this. Okay, so that would, of course, you can always write down the short exact sequence, but in some cases it's kind of silly. It's just the direct sum of this and this. When that is not the case, there's a non-trivial extension going on, and that's what we refer to as the short exact sequence not being split. Now here's a fun fact. For the Orbifold CFTs, as was observed in the paper written with McKelly, Robert, Shani, and Howe, we have just observed that, oh, look, it's very interesting that the 5D Orbifold CFT sees this kind of short exact sequence as well. Well, we've already figured out that this one is associated with D1, so it's a pretty natural guess to think that this naive defect group might be having something to do with the abelianization of gamma. Remember also in the 6D CFT context, the abelianization of gamma directly played a role. So that's the natural guess to be aiming for in this context. And then the C is kind of just the quotient that you get from modding this by that. does it work? So here's an example. We didn't do too many examples in the paper, but we did at least check it in a couple examples, and it seems to pan out like we'd expect. So we did an abelian case. And when you do that, 5D orbifold CFT, you find this kind of group action. That's the one I mentioned previously. Here's the short exact sequence. And notice that it's now a Z mod 2n that I'm writing here. So that's the kind of the naive answer. Here's the actual one form symmetry. And then if you quotient it, and if n is even, so n itself is even, not just 2n. 2n is obviously even, but n itself being even, then this thing does not split as an exact sequence. And it turns out that precisely when n is even, there's a gauge theory phase for this 5D CFT that you can write down. It's given by SUN, gauge theory at level n. And these folks here figured out what the global form of the zero form symmetry was going to be. It's not quite SU2, it's SU2 mod Z2, so SO3 in other words. So this would suggest that this Z2 fits with that, and everything is, matching up as one expect. So what we're exploring in this paper here is some further aspects of that kind of stuff. But let me just say, look for that in the future. And anyway, hopefully it'll be done soon. Okay, so I think I'm a little bit over time, so maybe I'll summarize and talk about future directions.
All good, you're good.
All right. So what did I tell you about? I told you about the defect group of 60 CFTs, but also 5D orbifold CFTs generated from these quotients of finite subgroups of SU3. I told you two different ways to calculate that defect group. Nothing to do with resolving the geometry or anything like that. One is involving the Quiver method, which involves just taking the adjacency matrix for the 5D BPS quiver, computing the torsion of the co-kernel, and that reads off the defect group for you in one shot. So that's very nice. And it can be applied in extremely complicated situations, so where gamma could be a very ugly non-abelian group. And in those kind of situations, it's very hard using alternate methods to kind of explicitly do all the resolutions and track what's going on with everything. This thing does it for you right away. I also mentioned a different way of doing it, just involving the fundamental group associated with the boundary geometry, 5-sphere mod gamma. And there we saw, again, something very nice. We kind of mod out by all the garbage of the fixed point locus, and we're left with kind of the electric one-form symmetry from this abelianization of gamma mod n. So for the future, I think two kind of very natural things to look at is, this is all great, but this was for the one-form symmetry. We saw hints that in the orbifolds, that it seems to know about via the group action's own short exact sequences. It seems to know something about two groups. So it'd be very nice to see in the geometry itself how those two groups are encoded, or if they're not, what hints that we have for the detection of the two directly from geometry. A lot of the methods in the previous literature, are using very sophisticated techniques from field theory to kind of piece together the answer using different pieces of evidence. But it'd be nice to see directly in the geometry how that comes about. And hopefully in this thing to appear, we'll address a little bit of that. And then of course, another kind of interesting piece to the story is, okay, great. So you've computed this two group. What is it good for? Right now, I would say the best thing you can use it for that I'm aware of is detecting various aspects of, like RG flows, if it has an anomaly and quantities like that. It's also, if you like, again, just intrinsic data to the field theory. I suspect that there's other very interesting applications of this, but that's kind of, again, something that needs to be worked out. I mean, these two groups show up in a lot of different applications also in like condensed matter settings. So there's no doubt in my mind that there are nice applications here in the higher dimensional setting as well. It's just, I think figuring them out is something for the future. Okay, I'll stop here. So thanks for listening. And, that's it.
All right, let's thank Jonathan. And do we have more questions? So, of course, yeah, go on.
I just had a very silly question, but it was related to this Armstrong theorem that you quoted. Is it in any way specific to S5, or is it just a general fact about orbifolds?
I think it's a general fact.
It's a general fact. Okay.
Yeah.
Yeah, I was just wondering if there was something with S5. Okay.
No, I mean.
Yeah,
so
no,
of course you know the answer for S3, and I'm pretty sure there's no problem with doing it for the other ones.
Yeah, okay. I was just wondering.
But my collaborators can correct me if I've misspoken. But I'm like 99% sure it doesn't.
I mean, for reasonable spaces, let's say.
how much work is needed to generalize this to toric Sasaki-Einstein?
So ones that don't look like orbifolds in particular.
Yeah,
Um,
yeah, the coniform.
Yeah, so in those cases, as far as I know, you have to, well, there's only two techniques I know of in that case. One is you do the blowups, or you just write down the quiver. So if you like, based on what you already did, Ami, in previous work, I can then read off the defect groups from those because you've already told me all the quivers I need.
I see.
So at that level, all I have to do is look at your old papers and I can start pulling out the answers.
I see. Okay.
But you can
So-
also compute it directly from the PQ web charges.
Correct.
The
Yes.
one-form symmetries.
From what?
From the PQ web, from the charges of the PQ branes,
I
you can
see.
just calculate the one-form symmetry.
Mhm.
And
Okay.
also actually the two group.
I think Greg has a question.
Yeah, just go for it, Craig.
I will just go for it. So if I understood correctly, you talked about both 6D and 5D essentially completely independently in this talk.
Correct.
So if you were to know that a certain C3 mod gamma orbifold theory can be obtained by compactifying a particular 6D theory on a circle, is
Yeah.
there something you can track about the defect group or so on through this compactification?
I would like to say yes, but I know in practice it's a little bit tricky to do this. So just as a simpler example, suppose I gave you a 6D CFT and I consider the operation of just tensor branch flow. So this is a deformation in Kähler moduli space.
Mm-hmm.
The defect group jumps all over the place when you do these decouplings of the curves in the base of. So for example, it will go from being like Zn to Zn minus 1 to Zn minus 2. So the
Mhm.
problem is that none of these are kind of subgroups of any of the other ones. Now, when you do the 6D to 5D statement, what are you doing? You're taking a limit in the Kähler moduli space for that Calabi-Yau threefold, such that you can kind of decompactify certain things. You might be doing other motions in the moduli space. So there's no a priori guarantee, as far as I can tell, that things are going to kind of behave in a kind of calm way as you go
I
down.
see.
I have more hope for things being nicely behaved under actually Higgs branch flows, but that's just kind of more of a. So for example, if you did a Higgs branch flow in a 6D CFT, in many situations, the base remains unaltered. So the defect group will kind of stay put.
Mhm.
And so I suspect that for Higgs branch flows, there might be a more robust story to tell that won't care too much. That's related actually to Sakura's previous comment about, you can sometimes just deform it. But there's also examples where we know that it could kind of screw up the value of H2 and H3, so anyway, I view it as something to do in the future.
I see, but it seems hard. Okay.
Well, I don't know if that's the exact. I think there's a variation on your question, which may have the property of like being like a subgroup or something like this.
Mhm.
But it's not just the most naive one where you just start decoupling things in the Kähler moduli space.
I see. Okay, thanks.
So I have a bit of a vague question, but just for what theories have these things been computed, these defect groups? Just in general, like what would be difficult theories, or where hasn't it been computed is maybe a better question.
Well, that's a time-dependent statement. I think like right now, one of the interesting.
I mean, right now, I'd like as of today.
I would say, well, there's certainly proposals for what to do. A lot of work has been done in like 3 dimensions, and I would say.
Oh, I meant 5D and 6D. Yeah, sorry, should have been more.
Oh, yeah. I don't know. I should probably not say too much about this because I think some of it is in progress right now by other groups. But I mean, certainly, for example, folks at Oxford have been, calculating a lot of these things for lots of different cases. It's, I mean, basically, you can track it back to like, this 2020 paper for when things started, where people started getting tools for calculating it. Basically taking the defect group that McKelly and I wrote down a while ago, and then, realizing that it could be generalized in this nice way. So, yeah, I would say that there's a lot of examples where it's calculable. I don't think, I mean, first off, I don't think it's been calculated for all the, well, so for 60 CFTs, there's a claim classification. I don't think it's known in all cases, like, directly how to extract it. In 5D CFTs, we don't even have a classification of theories. So, but of the ones that are known, I think that, at some level, it's just a question of like computational endurance. If you say that you know enough about H2 and H1.
Yeah.
So I don't know. That would be my answer. But yeah.
Very nice. You have more questions or comments?
So can you say some general words of once you have the computation of a large class of theories and you know the symmetries for them, what do you anticipate as a next step?
Right. So I think the next thing up would just start be calculating all the possible anomalies for those. I think that's like the natural next thing to do. So once you have that, then that would provide like a very helpful hint about what's going on with the strong coupling dynamics in many situations. I think that would be like if you could enumerate the entire global structure of the symmetries, I think the next thing up would definitely be to calculate the anomalies. At least that in my mind would be like the natural next step.
Okay, I see.
You hear me? Hey. I have one small comment on what Craig said. There have been some proposals for the actual 5D KK theories for 60 theories on a circle or on a torus. And I think that for those examples, it would be interesting to check if the defect group matches what you would get from a naive reduction. Right, okay. There was those models in which you see these gaugings of certain theories, class S constructions with some gauge group that were infrared free, or some somewhat exotic type of 5D theory. In those cases, it would be interesting to check, because those, if that is really the full 5D KK theory, the defect group should match. But only for that case. Otherwise, yes, it's impossible.
Right. Then I would also ask, well, once you know that, do you know how to track the changes in the defect group under mass deformations of that theory in some, I don't know, straightforward way? Although,
no,
again,
right? Because most one-form symmetries, for example, are emergent. Right? Like you start with the E6 theory, or whatever, EN theories, and then only once you actually decouple will you reach a theory that has a one-form symmetry, if you decouple to SU2 level 0. So in fact, right, if you think in terms of 60 theories, there are some which have already one-form symmetries, and or the defect group for the what you might call a two-form symmetry, that's something that descends to the 5D theory. But if you start with something that doesn't have anything, right, like the E string theory, for example, you'll find the one form symmetries appear, or the defect groups appear non-trivial at the bottom of the decoupling tree. That's where they populate stuff, right? So you start with TN, it's trivial, you decouple and you go to something that we call BN, and they don't have one form symmetries.
I see.
It's more emergent.
So you would say because they're emergent, there's no hope of being able to sort of understand them directly from 6 dimensions in some way. Okay.
Well, I don't know about that. I mean, you can track who's being decoupled, and you can watch how the quotient changes. So you can compute it case by case, but the point is, I don't think there's any kind of like clean conceptual.
There's nothing conceptual.
Yeah.
No.
Just like this accident happened. I went from Z mod n to Z plus 1 or so on. Okay, yes, you can do that, but but you know like why it was happening. So
right. Yeah. I mean, I guess the point I'm making is if you could say why it is happening based on the choices of mass deformations in some sort of, in principle sense, like you're saying, you know, mass deformations that satisfy this certain kind of pattern are going to lead to such an enhancement in the 5D theory and the deep IR. But
yeah, that would be great, but I don't know whether it's possible to make such a statement.
okay, yeah.
Okay, do we have more questions? Then let's thank Jonathan again.
Yeah, thanks.
That's very nice. Well, recording.